Welcome to this video exploring Young's double-slit experiment. We will examine the challenge of understanding light. If it acts like a stream of particles, why does it create a complex interference pattern? Thomas Young revolutionized our understanding of light. When he passed light through two narrow slits, he didn't see two lines on the screen. Instead, he observed an interference pattern of alternating bands, suggesting light behaves like a wave. Before Young, Isaac Newton proposed the corpuscular theory. This theory suggested that light is not a continuous wave, but rather a stream of billions of tiny, rigid, massless particles known as corpuscles. Newton's theory was useful for explaining how light behaves, such as reflection and refraction, by treating light as these tiny material bullets traveling at high velocities. Thomas Young challenged the corpuscular model. By demonstrating that light acts as a wave, he showed that passing light through two slits creates two coherent sources that ripple and overlap. This diagram illustrates wave interference. When waves from two slits overlap, they combine to form a specific pattern on a viewing screen, directly contradicting a simple particle-based model. So why the discrepancy? If light were merely particles, we would expect two simple stripes. Instead, we see an interference pattern, which confirms that light exhibits wave-like behavior. This visual representation shows the transition from a single light source to the creation of an interference pattern, highlighting how the wavefronts from two slits interact. To understand this, we define three key terms: the particle model, which views light as discrete packets; coherent sources, where waves stay in sync; and the interference pattern itself. Coherence is vital. For a stable interference pattern, light sources must maintain a constant phase relationship. This ensures the wave crests and troughs align consistently to produce visible results. When coherent light passes through these slits, we see the resulting interference pattern clearly. Constructive and destructive interference create those distinct bright and dark bands on the screen. If we look at the results, the particle model fails. Based on that model, we would only expect to see two bright lines, which does not match our experimental findings. The wave reality emerges when we observe the experiment. Light passing through the slits creates coherent sources, leading to the ripple effect that defines wave behavior. In this final overlap, we see that where wave crests meet, we get bright fringes, and where a crest meets a trough, they cancel out into dark fringes. In conclusion, the particle model fails to explain the observed interference pattern. Thomas Young's experiment proved that light behaves as a wave, creating a complex and beautiful pattern through overlap. And that concludes our discussion. Ready to keep learning? To master the next concept and get immediate access to our entire curriculum library, make sure you hit that like button, subscribe to the channel, and share this lesson with your friends. You can explore deep masterclasses right here on the global WaveEduAi channel, or find localized exam blueprints on WaveEduAi India and WaveEduAi Australia. Let's build your future, one lesson at a time.